Good morning, everyone. My name is Anna Smith, and I will tell you about our studies in Delft on the structure, thermodynamic, and thermophysical properties of molten salt nuclear fuels. Nowadays, nuclear energy is generated around the world by light water reactors, which are so-called generation 2 reactors, which run on a solid fuel. It's an uranium dioxide, a ceramic, and this fuel is cooled down by water, which operates at a temperature of around 320 to 350 degrees Celsius, meaning that the primary loop has to be pressurized. The energy from the nuclear reaction comes from the fission of the uranium-235, which, when it undergoes fission, produces fission products, a few more neutrons, and a lot of energy. And nowadays, we are looking at the next generation of nuclear reactors that could replace the current fleet of reactors when they come at the end of a lifetime. We are investigating so-called generation 4 reactors. And among these reactors, one of the design is called the Molten Salt Reactor. It's a very innovative design that is based not on a solid fuel, but on a liquid fuel and coolant. These type of reactors are very interesting. They are very promising. They present some inherent passive safety features. They can operate at low pressures, atmospheric pressure. They have a very great flexibility for the fuel cycle, and they show properties of good retention of fission products. I was talking about the fuel flexibility. Here in this type of reactors, in addition to the fission of uranium-235, we can also run the reactor on plutonium-239, which could come from stockpiles from civil nuclear energy or military stockpiles, but it could also run on thorium, which is a fertile element that becomes fissile uranium-233 after absorption of a neutron. So we do a lot of research on this type of reactors in Delft. And to run this kind of reactor, we need a liquid fuel with some specific properties. So we need to choose the fuel very carefully to satisfy some conditions on neutronic properties and things that I will talk about today related to chemical, thermal, and transport properties. We would like a fuel with a certain density, certain viscosity, certain thermal conductivity, but also a fuel with a high solubility of fissile elements. We want a fuel that has a low melting point, a high heat capacity, a low vapor pressure, or a high boiling point. At this moment, two types of salts are being envisaged among the MSR community. Some reactor designs are based on fluoride mixtures, and other reactor designs are based on chloride mixtures. Usually, there are 2 or 3, maybe 4 end members in these mixtures with a fissile element, for example, uranium tetrafluoride or plutonium trichloride, an alkali, a light, for example, here lithium fluoride, but it could also be sodium fluoride, potassium fluoride, or if it's a chloride, sodium chloride mixture, and maybe a fertile element if there is thorium in the mixture. So we are investigating this type of nuclear fuel, and why is it so important? Why is nuclear fuel chemistry so important? This is because understanding it is key for the good performance of nuclear reactors. The chemistry of a fuel will have an impact on the behavior during normal operation, but also during accidental scenario and accidental conditions. So really having a good insight on this fuel is key and at the heart of the progress of generation 4 technologies. Our approach in Delft is to perform some experimental measurements of phase diagram, of thermodynamics of the systems. We also look at the structure of the salt, and we couple this with molecular dynamic simulations to get more insight into the structure of the salt, into thermophysical properties such as density and viscosity. And once we have this information from experimental measurements or from simulations, we use that as input to develop some thermodynamic models as well as density and viscosity models that are coupled to the thermodynamic assessments. We do that for several binary systems, ternary systems, and in the end, we want to build a large database with multiple components, which will then allow us to perform application calculations to be able to assess safety scenarios as well as simply normal operating conditions. So today, what I wanted to show you to build upon the previous presentation by André Benesch from the GRC is our current effort to develop thermodynamic models that also describe the structure of a melt, the structure of a nuclear fuel salt. To give you a bit of insight on the structure of molten salt, if we have purely sodium chloride, you could say table salt, we expect to have a strongly ionic liquid. But as soon as we add uranium trichloride in a mixture with sodium chloride, for instance, we form a molecular type of liquid. We form monomeric species, complexes that can have various coordination. And these polyhedra will start to form networks. They will start to form chains that will really become predominant when the concentration of uranium chloride, in this case, increases. And now if we had in the salt mixture something like beryllium fluoride, then we could expect to form really a polymeric liquid. At high beryllium fluoride content in a mixture, we start to form dimers, trimers, and really polymeric chains when the concentration of beryllium fluoride increases. And why is this important? This is because the structure of the salt has a direct impact on the thermophysical properties. If we take viscosity as an example, we see that the viscosity in a mixture of lithium fluoride with uranium tetrafluoride or beryllium fluoride increases as the content of uranium or beryllium fluoride increases. But there is quite a difference between the increase in lithium uranium fluoride mixture, which is about 1 order of magnitude, versus several orders of magnitudes, as you see here, if we add beryllium fluoride to the mixture. So we really want to understand this relationship between the structure of the salt, the thermodynamics, and the thermophysical properties. How do we do that? We use experiments. We use X-ray absorption spectroscopy experiments, which are performed at a synchrotron facility, and that's because we need very intense and tunable X-ray beams. Since we also want to look at the molten salt, so a melt, we need to do high temperature in situ experiments. So we have built in Delft a furnace setup to be able to heat up our molten salt systems at high temperatures, and we bring this furnace to a synchrotron facility in Germany, where we measure then the X-ray absorption coefficient of a certain sample. So when we shoot some X-rays to a sample, we can measure the intensity before the sample and after the sample, and we, in this way, measure the X-ray absorption coefficient as a function of energy. What you see on this figure is an example of a measurement we did on a lithium fluoride, thorium fluoride mixture at 920 degrees Celsius. And in this kind of measurements, there are two regions of interest, the low energy region called the exanes and the high energy region called the exaves. It is this exave that is mostly interesting in this case. It gives us some information on the local structure around, in this example, a thorium absorbing atom. So we get information on the first coordination shell, the fluorine around the thorium, and maybe also the second coordination shell. Here is a picture of our furnace setup at high temperature with some detectors in front. And so again, this exave region. After some mathematical treatment of the data, we get the exave signal, and after Fourier transform, we get this figure, which is a bit equivalent to a pair distribution function, where thorium is here, and we see here the first coordination shell of fluorine around the thorium-absorbing atom. So when we fit this data, we get some average information on the local structure. We get information on the average distance between thorium and fluorine, in this case 2.3 angstrom, as well as the average coordination number. On average, we found out that there was, at this composition, 7 fluorine ions around each thorium. So that is already some information, but not a very detailed information. If we want more detailed information, we need to couple this experimental approach with molecular dynamic simulations. We do that using a so-called polarizable ion model that is really well adapted to ionic systems. And with these MD potentials, which we have, we can simulate EXAF data and compare to our experiments. This allows us to validate the interaction potentials of the molecular dynamic simulations. And in case there is a discrepancy, we can also fine-tune the interaction potentials to get a better agreement with the experimental data. With that, we have validated interaction potentials from molecular dynamic simulations, and we can then use the MD to get a detailed information and insight on the structure at any temperature and composition in the salt system, including in regions that we have not measured experimentally. We have followed this approach, for example, for a lithium fluoride, uranium fluoride mixture. And after the experimental campaign and after the molecular dynamic simulations, we could see that the chemical speciation of the salt varies a lot with composition. At low lithium fluoride content, we have mostly monomeric species of uranium fluoride that are 7-fold, 8-fold, and 9-fold coordinated. And when we increase the uranium fluoride content, we start to form dimers, trimers, tetramers, and eventually polymeric chains. So we have a fully connected network here. We then use this information to build our thermodynamic models. And how do we do that? We use the quasi-chemical model approach, which is also the one used in the GRC molten salt database that is really well adapted to ionic liquids. That is based on a description of a liquid with quadruplets. We know, however, that this mathematical description of a liquid with quadruplets allows to reproduce very well the phase diagram data, maybe also other properties such as mixing enthalpy, but do not give a completely physical description of a melt where we have molecular species that form, as well as an oligomerization of the melt, as we have seen from EXAFS and MD. So what we have done is to introduce a bit more structural complexity into this quasi-chemical description by introducing some cations with a certain coordination. We knew for the lithium fluoride, uranium fluoride system that we form at low lithium fluoride content mostly 7-fold and 8-fold coordinated uraniums. And when we increase uranium fluoride concentration, we start to form dimers. So we made a model of that system that included 7-fold coordinated uranium, 8-fold coordinated uranium, as well as dimers, we could say, that represents the formation of polymeric chains at high uranium content. In this way, we can have a thermodynamic model that reproduces phase diagram information, but also gives some insight on the structure of a liquid as we know it from the experiments and from the molecular dynamic simulations. So with this kind of description, we can also reproduce the chemical speciation from the molecular dynamic simulation. And this is what you see here, where the line, which is the Karlsruhe model, also reproduces the speciation of the monomeric species, the 7-fold and 8-fold coordinated uranium, as well as the progressive formation of polymers in this melt when the uranium content increases. So this is the first type of model I wanted to show today. And the second one is our effort to build models that couple thermodynamics with density and viscosity, since density and viscosity are also two very important properties for the operation of a molten salt reactor and for the safety assessment. What we would like is to use our thermodynamic models, which use the quasi-chemical formalism in the quadruplet approximation, to build models of the nuclear fuel that can also describe density as well as viscosity in a coupled approach. And here you have an example of our work on binary systems of lithium fluoride with uranium and thorium fluoride, as well as sodium chloride with uranium trichloride. So how do we do that? The density is related to the molar mass and the molar volume. And this molar volume can be expressed as follows. And this is an expression that was developed in the previous work of Robelin and Chartrand already some years ago. And so we have used the same approach and applied it to our nuclear fuels. So this molar volume is expressed as a stoichiometric sum of the molar volume of the end members plus an excess contribution, which represents the deviation from ideality of this molar volume. So this excess molar volume is related to the quadruplet distribution, so thus is related to thermodynamic model, as well as to the partial derivative of the excess Gibbs energy with respect to pressure. And this term is really the core of the density model, where we introduce some excess parameters, the beta terms here, which can be optimized and represent then this excess molar volume of this deviation from ideality. Once we have done that, we can go one step further to develop a viscosity model where we have a target function for viscosity that is expressed with a Nering type of equation, this one, related to Planck constant, the Avogadro number, as well as the molar volume. So here is again a link with the density model and the thermodynamic model. And then we have this exponential term with this G star, which is the molar activation energy for viscous flow, expressed as a function of the quadruplet distribution and some terms that are optimized in the model. So here again, you see that really we have a viscosity model that still is very much related to the thermodynamic description and to the description of density. We have done this, as I mentioned, for nuclear fuels. We have followed a Karlsruhe type of approach where first we need to build models for the end members, models for density and viscosity of uranium tetrafluoride, thorium tetrafluoride, and uranium trichloride. Once this is done, we can move on to binary mixtures where we describe the density in a binary mixture. And finally, we can go to higher order systems until we get description of density and viscosity for a ternary mixture. In this example, lithium fluoride, thorium fluoride, and uranium tetrafluoride. Finally, moving on towards more complicated systems, we have so far modeled fresh nuclear fuel, but of course, when fission happens, a lot of fission products are generated, which can be metallic precipitates, gas, or salt-soluble species. And we would like to know how that fission will impact density and viscosity of the irradiated nuclear fuel. So we need to build, in the end, a very comprehensive database for the density and viscosity of multi-component systems that can really represent nuclear fuel with fission products. And that's a work we are going to do within a European project called Endurance that just started about 6 months ago, where we will build thermodynamic models, density models, viscosity models of systems of fission products, so that we can build this large database for density and viscosity that will then be coupled to the GRC molten salt database presented just before. Finally, I want to acknowledge that this work was done together with my team in Delft. I have really wonderful co-workers. They're all listed here. And of course, we also have a lot of collaborators, and that work would not be possible without the collaborators. So we collaborate with people at KIT, INE for the spectroscopy measurements, our colleagues at the GRC Karlsruhe, at Concordia University, University Paris 6, and Orano. Finally, I would like to thank you for your attention and let me know if you have questions.